Hi, welcome to the Random Walk Simulations. In previous videos, we talked about what happens if we measure some quantity, which we call Q. The value we get from our measurement, which we call Q measured, will not be the same as the true value of that quantity, which we call Q true, because no measurement is infinitely precise. The difference between these two quantities, Q measured minus Q true, is the measurement's error. We want to look at this difference. In practice, the error, Q measured minus Q true, will get contributions from many sources. Here, we've written Q measured as Q true plus the effects of each error source for a given measurement. So here, each error source is represented by a yellow arrow. We said before that we're specifically interested in the case where there are n sources of error that are the most important, meaning that they are typically larger than the others. And these n sources are all of similar typical size. So as a first step, we will make a crude model of the errors to get a feel for how Q measured relates to Q true. We'll look at the n most important error sources, meaning the n sources that are typically the largest, and we will neglect the rest. We will take them all as having the same constant size, but we'll take their directions, i.e. that they can be positive or negative, to be random. So under this crude approximation, we've now written Q measured as equal to Q true plus n error sources, drawn here as yellow arrows, which are all the same size, but which are randomly up or down. This implies that to get from Q true to Q measured in this crude model, we'll be calculating an n-step random walk. We'll start with n equals 1 and then move up to the cases of n equals 2, 3, 5, and 15 steps. We'll do simulations of these random walks to highlight their random nature. We'll also look at the average expected results for each case. Okay, let's start with the one-step random walk. We'll start with this case because it's simple and will let us cover the basics. This represents the case where there is n equals 1 important source of error, or in other words, all other sources of error are typically much smaller, so we can ignore them. So Q measured is equal to Q true plus the error, which is either positive or negative. So take this chevron. We're going to drop a ball on it. The ball will roll left or right with equal probability. We're taking these balls as independent. That means that whether one ball goes left or right does not change the probabilities of the other balls going left or right. Okay, we'll drop 100 balls. Each dropped ball represents a measurement with one important source of error. If the ball goes to x equals minus 1, and thus goes in the left bin, that represents a case where the error source was negative and Q measured was less than Q true. If the ball goes to x equals plus 1, and thus to the right bin, that represents a measurement where Q measured was greater than Q true. Because the probabilities to go left or right are equal, we expect, on average, 50 in each bin. But that's an average. The actual result will be statistical in nature. Okay, so now that all 100 balls have fallen, we can see that we have 52 in the left bin and 48 in the right. This represents doing 100 measurements and having Q measured pushed down by the error source in 52 of them and pushed up in 48 of them. These results are statistically consistent with the expectation that we would have, on average, 50 in each bin. Okay, now let's move on to the two-step random walk. Okay, so here we have the n equals 2 case. We'll drop 100 balls. Again, each dropped ball represents a measurement, in this case with two important sources of error. The first step represents the first source of error. The second step represents the second source of error. Let's see what we expect on average while that simulation is running. After 2 steps, the possible ending locations for the ball are x equals -2, 0, and x equals +2. There are 4 possible paths for the ball to take. The ball can go right toward positive x twice and end up at x equals +2. This represents a measurement where both sources of error pushed Q measured up from Q true. Alternatively, the ball can go left toward negative x twice to end up at x equals -2. This represents the case where both sources of error push Q measured down. And there are 2 paths where the ball goes left once and right once. One path is highlighted in yellow and the other in blue. These represent the 2 cases where the error sources push Q measured in opposite directions. For both of these 2 paths, the ball ends up at x equals 0. All paths are equally likely. Because there are 2 paths going to x equals 0, the ball is twice as likely to end up at x equals 0 than at either other location. On average, half the balls end up in the middle. 1/4 end up at each end location. Here, we'll just note that there are more paths that lead to the middle of the distribution. We will see more of this later in the video. Anyway, we dropped 100 balls. We expect, on average, to have 25, 50, and 25 in the 3 bins, respectively. In this run, we got 25, 56, and 19. This is statistically consistent with what we would expect on average. This represents doing a measurement 100 times, where, in 25 cases, both error sources pushed Q measured down. In 56 cases, the 2 error sources pushed Q measured in different directions, and in 19, both error sources pushed Q measured up above Q true. Okay, now on to the 3-step random walk. Here's the layout for the 3-step case. We'll drop 200 balls. The possible ending locations are x equals -3, -1, +1, and +3. Note that for an n-step random walk, there are 2 options for the ball at each step, left or right. So the number of possible paths is 2 to the n. Here, n is 3, so we have 8 possible paths. One path leads to x equals +3. One leads to x equals -3. There are 3 paths that lead to x equals +1, shown here in yellow, red, and blue. There are also 3 that lead to x equals -1, which are the mirror images of the paths shown. So on average, the ratios of the number of balls that end up in each bin will be 1 to 3 to 3 to 1. For 200 balls, like we're dropping here, that corresponds to 25, 75, 75, and 25 on average. Note that most balls end up in the middle, as more paths lead there. This will be a continuing theme. In this run, we had 31, 73, 74, and 22 balls in the respective bins. Here's how those results, both what we obtained here and the average, come into the relation between Q measured and Q true. Most of the time, the errors partially cancel, like we saw in the 2-step case. And the results we got in our simulation were reasonable given what would be expected on average. Okay, let's move on to the 5-step random walk. Here we'll drop 300 balls. The possible ending locations range from x equals -5 to x equals +5 in steps of 2. It's now getting too complicated to show all 2 to the 5th or 32 paths. but we'll say that the numbers of paths leading to the possible ending locations are 1, 5, 10, 10, 5, and 1, respectively. We'll plot the probability as a function of ending location. So here is the probability of a ball ending up at each possible location. We said there were 32 possible paths, and the numbers of paths leading to the bins were 1, 5, 10, 10, 5, and 1, respectively. So the probabilities plotted here are 1 30-second, 5 30-seconds, 10 30-seconds, etc. We didn't go through explicitly how to calculate these probabilities, but if you want to know more, check out the binomial distribution. Now, we can't claim that this plot looks like a Gaussian function, but the probabilities are peaking in the middle of the plot and comparably smaller in the tails. This peaking behavior comes from the fact that while all the paths a ball could take are equally likely, there are more paths that lead to the middle of the distribution and fewer that go to the tails. And that means that in a measurement, it is most likely that the number of sources of error that push Q measured up and the number of sources of error that push Q measured down will be similar. It is unlikely that all or almost all of the sources of error push in the same direction. For 300 balls, we can take the probabilities that we saw and multiply by 300 to get the average numbers of balls expected in each bin. This run had good agreement with the average expected numbers. Okay, and lastly, a 15-step random walk. Here we'll drop 400 balls. The possible ending locations for a ball range from x equals minus 15 to x equals plus 15 in steps of 2. Here we'll just plot the probabilities for a ball to end up in each possible location. We can start to see a Gaussian shape emerging. In fact, we can plot a Gaussian curve on top of it, scaled by a factor of 2 to take into account the empty bins. The fact that the distribution is approximating the Gaussian curve is clearly visible. We won't go through the individual bins, but this run of 400 balls is in reasonable agreement with the average expected numbers. Again, we can see that the cases where the sources of error mostly cancel each other are the most likely. Those where all or almost all of the sources of error go in the same direction are rather unlikely. Okay, let's give a quick summary. We see that as the number of steps n gets large, the distribution of ending locations of the ball starts to look like a Gaussian distribution. The distributions of ending locations peak near x equals 0 because there are more paths leading to that region than to the tails. We're using this as a crude model of measurement errors, where there are n dominant sources of error, which are all of about the same typical size. This means that in our crude model, the error Q measured minus Q true becomes Gaussian-like as n gets big. Next, we'll see a more realistic depiction of measurement errors by letting the step size vary. We'll see the Gaussian behavior emerge more easily, and we'll be able to apply it to a real-world case, rounding error.